Hello fellow problem solvers, so they're going to be doing a problem from the Junior Balkan Math Olympiad 2017, problem number 1. I suggest you try to smash problem out for a minimum of 10 minutes, ideally 30 minutes to 90 minutes, not more than 4.5 hours. And I say not more than 4.5 hours because if you were at the JBMO and you had nothing else to do, you'd need to do this problem, right? Unless maybe you like geometry more or algebra, in which case you might skip. And if you're just, practicing, preparing for a junior level competition, try this problem out ideally for about 2 hours at most. I think it's an hour long problem. So without further ado, let's begin. The first thing I want you to do, if you want to attempt this problem with us, is I want you to pause for like 5 minutes and see what is the problem asking. So pause now. And it's asking you to say, determine all the sets of 6 positive integers. I pick 2, I take their product, I add to another 2, I add their product, and I get the product of the remaining 2. Okay, so let's see what this sort of looks like. Could n be like, say, 100? If we have like 6 consecutive integers, could we have 100 to 101, 102 to 105? Let's pick a biggish number, right? A decently sized number, actually, 100. So if you're like, when you have infinity, what is a big number? But anyways, what do we have here? Well, if I take the product of any 2, add a product of the other 2. Actually, if I take the product of some 2, I'll get something around 10,000-ish. But if I pick the product of any 2 of these numbers, right? 105 times 104 is still around, 10,000-ish, maybe 11,000 at most. But if I add to around 10,000-ish, I'll get around 20,000-ish. So this won't work for 100, just due to size differences. And with this idea, I invite you to pause for another 10 minutes and try to push the problem further. And here's the next step. So after playing around maybe with a couple of these numbers and figuring out, wait a second, this isn't going to work out often, you see, like, what's the problem? If your numbers are n plus 1 through n plus 5, what do you have as your biggest sum? Your biggest product, actually, like you're going to take 2 numbers in a product, is going to be n times n plus 5 times n plus 4. This is the biggest one. The smallest sum of any 2 is going to be n times n plus 1 plus n plus 2 times n plus 3. I think this is the smallest one, right? And you can see roughly here, this is going to be n squared plus 9n plus 20. And this here is going to be 2n squared plus n plus 5n. So I'm just like now trying to check out if there's a different if I combine them differently. I don't think I would get anything that's smaller. And we would need to maybe say a couple of words for why this is. Why is n times n plus 1 plus n plus 2 times n plus 3 the smallest one? Why is it not n times n plus 2, n plus 1 times n plus 3, or this times this and this times this? Do I think that argument shouldn't be too difficult? Because it seems like, wait a second, so whatever I do, will I get 6n here, right? If I do n times n plus 2, I'll get 2n, and then n plus 1 times n plus 3, I'll get 4n from there, 6n. So I'll get 6n no matter how I switch them around. So the only thing is, like, how can I get the lowest number? When I multiply these out, and that might be actually n plus 1 times n plus 1 times n plus 2, n times n plus 3. So actually, this isn't the smallest. It might be n times n plus 3 plus n plus 1 times n plus 2. But we can check them all out. But roughly, it's of the size 2n plus 6n plus 6. And this smallest possible, right, among any of this, say, left-hand side, needs to be greater than or is going to be, needs to be less than or equal to the biggest possible I can have on the right hand side if I'll have equality for this n. And let's actually see like what are the other options for n times n plus 2. And maybe here's a place where I could also invite you to pause and see like what is the smallest possible sum. Pause for the next 5-10 minutes and see if you can push the problem further, take it further. And here's the next step. So I do this. I'll get again 2n squared, 2n, 1, 4, 6n, and then I'll get times 1 times 3 plus 3. And I'll get n times n plus 3. Yeah, this is going to give me the smallest one, I think. N plus 1 times n plus 2. It's really like, sometimes your intuitions just don't match up to reality. And that's why it's good to like double check these things. Okay, so this is the smallest one, right? And it has to be the smallest one. You need to pick the 4 smallest ones. Otherwise, if we had n plus 4, not one of the 4 smallest ones. That I think is sort of explanatory that these have to be part of the smallest sum here. So this is the smallest thing, like if we're going to have a times b plus c times d is e times f. E times f is at most n squared plus 9n plus 20. And this thing here is at least 2n squared plus 6n plus 2. So now we need this to be greater than or equal to this. Why will this not always be the case? Well, because n squared will get on this side and n squared sort of grows faster. So we have now, this is true if and only if. So we get rid of this. 9n becomes minus 3n. So n squared minus 3n. This is plus 20. Plus 20 becomes minus 18. If and only if this is true. Now there's a way, actually, we can just factor this out as n times consecutive positive integers. I just wanted to check that. This is n times n minus 3, less than or equal to 18 also. I'm trying to find a way so that I don't have to like solve a quadratic. Actually, though, can I factor this? 6 times 3 maybe. Oh, actually I could. N minus, so it might be n minus 6 times n plus 3 less than or equal to 0. Needs to hold true. Given this is positive, this needs to be less than or equal to 0. So n needs to be less than or equal to 6. And here's a good place for you to pause for the next 10 minutes and try to understand what it is we've done. And see if you could push the problem further. And now here's the next step. So now what do you do here? You have n is less than or equal to 6. And you want to see, now we can do casework now and show that, so for n equals 6, we'll need to have n plus 4 and n plus 5 on this side. And I'm thinking, is there a quicker way than just like doing casework? So we need to determine all sets of 6 consecutive positive integers. I mean, let's just see like what happens. 1, 2, 3, 4, 5, 6. What will I ever do with these numbers? Like the only idea for me right now is casework. I do not see another way to go about this. Maybe if it's 5 times 6, I need 30. And 30 is just too big. Seems 4 times. 4 times 3 times 2 times 1 will be too small. So that one isn't going to work. Maybe actually I could maybe do them into cases like what is on this side of the equation, and then that could also, like if it's n plus 5 times n plus 4, maybe then maybe this forces, so for n equals 6 I'll have this is equal to 0. So for n equals 6 I'll have this set what is it, 6, 7, 8, 9, 10, 11. 10 times 11 will be 6 times 9, 7 times 8. Like it should be if I've done the math correctly and if I haven't messed anything up. 6 times 9 is going to be 54. 7 times 8 is going to be 56. 54 plus 56 is 110. So this set works. of consecutive integers. Now, can I make changes to it? So if I have a 5 instead of a 11, 5, 6, 7, 8, 9, 10, I'll have, say, so 90 can't be the thing. This is the biggest one. Maybe 10 times 8. Also, okay, so here now, modulo 5, if I'm looking at this, if I have 10 and 5 that are away from each other, they're not in the same thing, it won't work. Like they're not part, if it's not 10 times 5 somewhere, this won't work out. So we need, because then two things will be divisible by 5, the second thing isn't. I think we might have to just do this case by case now. So two things might be divisible by 5, the other one is not, so we need to have 50. And then it's 6 times 7 is going to be, it seems like the product, the smallest, no matter how I pick these two, they won't add up to 50. And I think the way to say this is because 9 times 7 is, if I pick any two pairs of these, I think the smallest product is either 9 times 6. 9 times 6 is 54, 7 times 8 is 56. Yes, 9 times 6 is the smallest possible product. So we'll have 50 plus something is equal to something. That something is at most 8 times 9, which is 72. And this other thing is at most, at least 42. So this fails because it's not equal. So maybe this case doesn't work out. I'm really curious, is there another way? Also, why did this not work out? Let me see if there's a module. Now, this is the thing you do with number theory. You see there's a module that tells you, there's a modular arithmetic that can tell you why it doesn't work. And one is divisibility by 3, say here, actually. Divisibility by 3 makes it now work. Because here I had 6 times 9, everything divisible by 3 was here. Maybe that is going to be a thing. I need to have 6 and 3 be together. So I need to have 18 here, because both are divisible by 3. And then what can I have? I can either have 20. So yeah, I can have 18 plus 2 times 1 is equal to 20, which is 4 times 5. So this triplet works out. And then again, for the triplets 2, 3, 4, 5, 6, 7, I need to have 3 and 6. I need to have 18 as well here. And then I need, for the other numbers, it's like the absolute value of a times b minus c times d needs to be 18. Like that's sort of the equivalent formulation here. So what can we have? Can we have, I hope we can, it's not just a lot of casework. And I'm thinking I'm missing something dumb. So this is, okay, 7 times 4 is 28. So 18 plus 2 times 5 is 7 times 4. Is there a connection between these two? 3 times 7, 4 times 5, and then going to 2 times 5, 7 times 4. Actually, wait a second. Oh no, this is 2 times 1. My bad. 2 times 1, 4 times 5, 2 times 5, 7 times 4. I don't really see a connection just yet. So let's go further. Now it's 3 through 8. Like we'll get here from both sides. 3 through 8, we're going to have, it's actually so interesting. So here's 6, actually here's 6 and 9 need to be together. So I could have just said like, we're going to have 6 times 9 is 54. The 5 and 10 need to be together, so we're going to have 50, and then 7 times 8 is forced to be 56. And none of these two add up to another. Now for 3 through 3, 4, 5, 6, 7, 8, I again need to have 18. I'm looking powers of 2, actually, 18. I'm now looking at powers of 2, powers of modulo 7, modulo 5. It's just like you're trying to figure these things out quickly, is I think the issue. So 8 times 7 is 56. That'll be too big. And I would literally need to write this down on the contest if I was competing. So 32, 32 and 33. So that doesn't work. 8 and 4. Yeah, 8 and 5 is 40. This is 28, so this one doesn't work. And I'd say 3 and 6 need to be together, and the rest is case by case analysis. There's not much more I can do here. I mean, I don't see much more than this. Then it's 4, 5, 6, 7, 8, 9, and this is the final one. So 6 and 9 now, looking at divisibility by 3, need to be together, and this is 6 times 9 is 54. And then what do I have? I can't have these two. 8 times 7 doesn't work because then this is 56. 20, you can't combine them in any way, shape, or form. This is 40, this is 28. Oh, so close. 64. Too bad, too bad. Though actually, wait a second. Is that 8 times 5 is 40? I get 4 out. Wait, how do I get 64? I'm a bit confused. 7 times 8 is 50. 7 times 5, 4 times 7. 8 times 5 is 4 times 10. 4 times 10, I get the 4 out. 10 plus 7. I'm so confused. Wait, this is 40 plus 20. Yeah, 40 plus 28. Why did I think it was 40 times 24? Never mind. This doesn't work, and the final one is 32 plus, say, what's it called? It doesn't work because it's evens and odds. So that seems to be it, right? This set works. We've shown that this set works, and this set works. And we've said n needs to be less than or equal to 6. Otherwise, we have bounding issues. And this finishes up the problem, really. This is really a case by case that you would need to write down. And what I like about this problem is that you have this sort of, you're trying to, like, you can do immediately once you get n less than or equal to 6, you can write down all the possible cases. And I think, okay, first thing is you need to take these words, put them into some algebra, number theory that you can actually work with, right? To actually prove something. That is your first sort of step. And after you've done that, then you have a sort of a bounding thing, which is, decent, nice, okay, it's a good idea. And then that gives you like n needs to be less than or equal to 6. And then you have the casework. Now, there's going to be a lot more casework if you don't figure out something around divisibility by 3 for the cases that don't work. And I think 3 cases we found just did not work. But because we had the divisibility by 3 sort of figured out, 2 are going to be divisible by 3, then we had, okay, that means this. And then things were a lot simpler. Like because one number was fixed, like the 6 times 3 or the 6 times 9, that was fixed. And the other 4 numbers had to make that somehow. So I think that's what's interesting about this problem. And it also led us to solutions, right? Here we could have just seen, okay, we need 18. And then you're basically done. So this finishes up the problem. I really like it. And as always, thanks for problem solving.